Welcome everyone to this problem solving session of this course named Basic Thermodynamics. Uh, I am sincerely apologetic about the mishap that happened the last session. So it was for a technical issue that my audio couldn't be captured, and probably you guys have faced some issues about that. I hope. But the good part is today's problem solving session is just like similar to the problems that we have discussed in the previous session. So if you guys have the problem, hi Tathagato.
Hello, sir.
Hi, I was just discussing about that the previous session, my due to some technical issue, my audio couldn't be captured, and I am sincerely apologetic about that. And I will be careful for the future sessions. And I don't know what happened, but probably the good part is today's problem solving session is just extension of those problems. So those counting problems and the probability calculations, all things will come up. So I hope that you guys didn't have any problem, but if you have any problem we can discuss about it. And on top of that you have the PPT, and there you have all the detailed calculations, so that thing is covered, I guess. But
I don't think it will create any problem.
okay, great. But if you have any problem you can discuss those things in this problem solving live session. And that's it. Just wait for 1 or 2 minutes others to join, and then we can start our usual
Okay,
session.
sir.
Okay, let's start. Okay. So from the previous class you have got some idea about how to calculate the microstates, how to because those things are based on the counting problems, and the basic concepts those of those things actually come from your permutations and combinatories things of your class 12 mathematics. But you have to just extend the idea, and you have to count it in such a manner that it fulfills the criteria that is given. And on that same spirit, let's start this session. And I will just give you one heads up that this problem solving session and the problems that is there is just like this previous problems, but here you have to we are considering different kind of energy levels, different kind of statistics, so that thing will come into the picture. Okay, without further ado, let's start the session. Okay, so welcome again to this problem solving session. This is the we are coming to the like end of this course. So this is week number 8. probably 2 months long. We have all done this session. So congratulations to everyone. Okay, so this course named is as Basic Thermodynamics, Classical and Statistical Approaches, and the instructor is Professor Arnab Mukherjee from IIT Pune, and I am Dibyendu. As you all know, I'm a Prime Minister Research Fellow in IIT Kanpur, and I work in the field of soft and active matter physics, where I study different non-equilibrium statistical mechanics phenomena. Okay, so this is the link of my website. If you get interested in my topic, you can contact me, or you can mail me at any point of time. We can discuss. And all the lecture sessions that has been discussed here and will be discussed here will be uploaded in this YouTube channel, and there is a dedicated playlist in the NPTEL tutorial session of this course, and you can find all the live sessions there. And if you like the content, and if you like if you appreciate my effort, please leave a like or leave a comment there. I will be highly thankful to you. Okay, so let's just start. Okay, the first problem says, in how many ways can we distribute 5 energy quanta, okay, 5 energy quanta among 9 particles such that there can be only 1 quanta per particle? Okay, so Tathagato, do you want to give some try, or think about it loudly, or like discuss with me how can you tackle this problem?
So here we need to distribute the energy among 9 particles.
Yes.
5 energy particles, let's say 5 A, B, C, D, E,
Okay.
things are there. We have to distribute among 9 particles.
Okay, so just as you have just said, let's write it. A, B.
So there is a restriction that only one quanta per particle.
Exactly. So there are 9 particles. So can you? So okay. So just let just try at first. Then okay. So then, if the condition is only 1 quanta per particle, then what can you say from this? That there will be always 4 particles which will not have any quanta available, right?
Yes.
So then how can you solve it?
Out of 9, only 4 particles cannot have any energy at a particular time.
Perfect. Then
9C4.
yes, that's the answer. Right. Okay. So the 4 particles will always be left with no quanta. Then the problem boils down to this. That choosing 4 particles out of 9. And since there is no other thing that distinguishable or indistinguishable, we can just write 9C4. And what is 9C4? 9 factorial divided by 4 factorial divided by 5 factorial. Then it becomes 9 times 8 times 7 times 6 divided by 4 times 3 times 2 times 1. So this cancel out, this to this. So 14 times 9, what would be?
126. Option A.
Hi Mukhilan.
Hi, sir.
Yeah. Okay. So we are just discussing about this problem. So this problem says, in how many ways we can distribute 5 energy quanta among 9 particles such that there can be only one quanta per particle. So as Tathagato just helped me to solve this problem, he said that since there are 5 energy levels and 9 particles, and the restriction is only one quanta will be available for particle, then 4 particle will always be there with left with no quanta. So now the problem will boil down to choosing 4 particles out of 9. So that is this problem, right? Choosing 4 particles out of 9, these 4 particles will be left with no quanta. So how can we choose 4 particles out of 9? That is 9C4, 12 mathematics, class 12 standard mathematics, 9C4. And if you do that, then 9 factorial divided by 4 factorial divided by 5 factorial, that gives you 126. Okay? So,
Okay.
okay. So this right option will be this 126. So we can distribute the particles in. Okay, no problem with that. Can I proceed to the next problem?
Yes, sir.
Okay,
Yes, sir.
okay, great. So the next problem says, calculate the number of ways of distributing 3 distinguishable particles. So here it is clearly mentioned that is distinguishable among 4 distinguishable energy levels, and there is no restriction on occupancy of the energy state. So any clue how can you do it? Anyone? Don't be scared, just say it, just think out loud so that I can help you in thinking. And you know what happens, that when you are thinking and you are going in wrong way, and I can correct you, and that thing will always be with you, and you will always, whenever in the future you will always do some problems in that way, you will not never, you will never go. So that route, that wrong route will always be closed. That's why always it is important to think out loud, because this is a problem solving session. We can discuss about it. There is nothing wrong in giving incorrect answers. Okay, I'm giving you one hint. Okay, one or two hints, then you will help me to solve it. Okay, so that says that there are 4 energy levels, right? 4 energy levels. Let's write these 4 energy levels. Let's mark it A, B, C, D. Okay, and 3 distinguishable particles. 3 particles. Let's say one asterisk, one has, and one ample is at the end. Now, can you map this problem with dice problem? Because in dice, what do you do? In dice, there are 6 faces with 6 different numbers. Let's just assume there is one dice or one coin which has 4 outcome, A, B, C, D. Means in coin toss there is 2 possibility, head and tail. In dice there are 6 possibilities. 1, 2, 3, 4, 5, 6. Here you can think like this. This always choosing energy level, there can be four possibilities: A, B, C, D. Now, since there is no restriction on the occupancy, then it can happen that always 3A can happen, or 3B can happen, 3C can happen. Means all the particles can be A, can be B, can be in C, can be in D, like that. Or it can happen in such a way that one particle in A, one particle in B, one particle in C, or B, C, D, or two particle in A, one particle in B. So now with this clue, can you answer it? What will be the possible arrangements? Anyone? Just try to give this answer. Now if you flip a coin 3 times, 3 particles means here it will map to 3 times coin tossing. What is the possible choices, possible ways of outcome? 2 to the power 3, right? 8 in coin tossing. There will be head, tail of, let's do like this: head, then it will be head, tail, then it will be head, tail, head. Like
So this will be 4 to the power 3.
Yes, that's the right answer. That is the same
So
problem,
we
right?
are just
Tell me.
taking the 4 energy levels as a 4-faced die.
Yes. Yes.
This approach I'm yet to apply in real life. I mean,
This is pretty simple, right? So always you have to do what you have to do. You have to map the problem which is in physical problem and try to map with your known system. That will make your problem easier, and that will actually make you think the problem in a simpler way. Okay. So that will be 64. So this will be this. Now I have one simple question. Yeah. Do you have any comment? Please tell.
so basically it is asking the number of possible outcomes.
Yes. Number of possible outcomes, right? That is the possible distribution, right? Yeah. Because when you are flipping a coin 3 times and you are saying that these are the possible outcomes, that means that how can you distribute head and tails in three trials, right? That's the same thing. Exactly, right? Now I have one simple question. Why isn't it like 3 to the power 4? Like you can say like 3 particles, 4 energy levels. So you are doing this 3 to the power 4. So if you answer this question, then like choosing 4 faces of dice and mapping them to this kind of problem, it will be easier. So that's why I'm trying to, this is nothing to do with this problem, but I want you to think like that, so that in your future, in your every step, you can like apply those concepts, and you can apply these concepts in your real life, right? So why isn't it 3 to the power 4? Why is it 4 to the power 3? Yeah, Mugilan, please. Hello. Yeah, your voice is breaking, but yeah, now I can hear you. Please say.
Yes, sir. So what if the particles are actually indistinguishable?
Yeah, that's a very good question. If the particles are indistinguishable, then there will be no other thing like that. Then we have to calculate, like how can we distribute 3 particles in 4 energy levels. That thing will come into the picture. So one thing we can do is all the particle will be in one thing, means one energy level, and that can happen 4 ways. Means like all the 3 particles can be in A, can B, and C, and like this. Okay. So now the thing is, if this is 2 1, then this problem will become like choosing two boxes, 2 energy levels which is not filled, right? And then how can one box, or how can A and B, let's just simplify it. This is a good question. Okay, so this is, what if we have some problems in later stages. What if particles indistinguishable? Okay, so one can happen that all the 3 particles will be in same place. That can happen in 4C1 process, in choosing one thing. And one can happen then 1 is 2, 1 is 1, means 2 particles can be in one arrangement and 1 particle can be in another arrangement. And that can happen like choosing 2 empty energy level out of 4C2 times, and they can actually rearrange, means if it is
Interchange the places.
interchange with this thing, that can happen like 2. Okay, this can happen in that way, or it can happen 1 1 1, means each levels 1 and 1 will be empty, and that is similar to 4C1. So these will be the possible outcomes. Okay, is it clear, Mugilan?
Yes, sir.
Yeah. Now answer my question. Why isn't it 4 to the power? Why isn't it 3 to the power 4? It is 4 to the power 3.
Actually, here we are setting up 4 energy levels, and we
Okay.
are assigning each energy level to the 3 particles.
Okay.
So in a way, the outcomes are 4 energy levels, number of outcomes.
Okay. Okay. Please, continue. We are going in right way.
The number of outcomes are 4. That is the energy levels, and the outcomes come with respect to those of the 3 particles. Like
Yes.
in case of a coin toss, the outcomes are only 2.
Yes. Right.
And for a single time coin tossing, so
Yes.
as a coin tossing is a single, the event is a single event, so
Yes.
the whole to the power, the exponential term is only 1. So here
Yes.
also, since the thing is since the particles are of 3, so here it
Yeah.
comes out to 3.
So just in a nutshell, what Tathagata said is quite right. In a nutshell, if you have to describe in physical term or in mathematical way, that when we are assigning one energy level to the particle, that is equally probable, right? But when we are assigning number of particles to the energy level, that is not equally probable. Means equally probable, the probability of being like, if you think in that way, that here you are assigning particle in box. If you assign box in box where the particle will be, then that thing, it can happen in such a way that this particle, can you see my cursor or not?
No, sir.
No. Okay. Just a minute. Now is it visible, right?
Yes, it is visible.
Okay. So here our problem
Yes,
is,
sir.
yes, here our problem is that choosing one particle and assigning them one energy level, and this energy level are equally probable. Now if you think like that, choosing one energy level and assigning particle to that will not the same thing, because here the choosing number of particles in that way will not be equally probable, right? Because here we are just, what we are doing, we are just multiplying, means like multiplicity is there for each particle, but multiplicity is not there for energy levels. Is it clear? Or
we cannot assign two energy levels to a particular particle.
exactly, right?
But we can place two particles in a particular energy.
Yes, that's the thing. So this is the fundamental difference that you have just picked it up. So that fundamental difference is now in research or in academics, where you will go, choosing that fundamental thing will always help you. So here, just as Tathagata said, that we cannot assign two energy levels for one particle. That is contrary to our physical sense. That's why you cannot write 3 to the power 4. That is equally probable. That is not equally probable when we are in the case of energy level, right? Okay.
Yes, sir. The thing is, I can understand things, but I cannot apply to questions.
Yeah, that will come. That will come with practice, because you have to do lots of practice. Okay,
Yes.
lots of practice, and always think like that. That you take one problem and you just play around those problems and try to think about it, how you are doing this. Because as just Mugilan said, that what if the particles are indistinguishable? So this kind of questions should always be there, and then you think about it, because this is not possible that there will always be some people or some professors or some sirs, some tuition teachers that will help you. You have to think on your own, and after thinking those things and after thinking out loud, you will see that you have grown some confidence in your mind or in yourself, and then you can apply yourself in this kind of problems. Okay.
Yes, sir.
Yeah, that's the motto. Okay, should we proceed to the next problem?
Sure, sir.
Okay, so this is an interesting problem. Problem says 5 distinguishable particles are to be distributed among energy levels such that their total energy is 5e. Okay, how many distributions are possible, and what is the total number of ways? So for such distributions, so if you think in this way, so here this is the distributions. This is the distributions. This is called macrostates. Okay, this is the distributions. But in that distribution, there is always any other different kind of ways, right? 4c1, 4c1, 4c2 into 2, 4c1. So these are the ways.
Number of ways.
Yes, this is the distributions. How are they distributed? Okay. Okay. So can you answer it?
So here is no restriction.
There is some restriction that total energy is 5e.
Yes, I mean the distribution thing, there is no restriction.
No restriction, yes. Just take 1 or 2 minutes, and Mugilan, you also try, and then you can share your idea and we can solve that problem.
Hey, here one thing is not mentioned, that each energy level consisting of how much energy? E.
That is up to you. It can happen that it shouldn't be negative. Let's just give you one thing. It can be 0. It can be 5e. Maximum it can be 5e, right? Energy level maximum.
Yes, total.
0 to 5e, you can just have to choose it.
Okay, so if I choose 5e, then 4 particles can be in 0 and 1 particle in 5e.
Exactly. So how many? That is the distribution. So let's write distribution first. So let's say distributions. Okay.
So here we need to, do it physically, so that
Yeah, yeah,
otherwise it is
yeah, yeah.
a bit tricky.
Bit tricky, yes. Distributions will be. You said that one particle.
Is in 5e and the other 4 should be in 0 because the
Yes,
total energy should be 5e.
yes. In
It is very similar to that. This energy formula is very similar to like that simple harmonic oscillator quantum
yeah, yeah.
degeneracy
Same,
of
same
those.
thing. So I will write in this way. Okay. So 5e
Plus
0
0,
0
0.
0 0. So next possibility, please tell me.
1 4e,
1 4e
1e rest all 0.
1e less all 0. Other one?
The reverse e 4e.
No, that I will put. This is the distribution, right?
Okay,
So
okay, okay. So 3e,
then
e comma e.
rest as 0.
Uh,
Then any other?
yes, yes, 3e comma 2e comma 0 0 0.
Yes. Again, any other?
2e,
2e
2e,
2e
e
e.
0 0.
Any other?
E comma
2e,
E comma E comma E
Yeah, Mugilan, you are saying something. Please say.
comma. I mean, one E for each.
Yes, that is another possibility. Any other?
One 2e and
1 2e.
3e
That is
and
there,
3e.
right? That is there, right?
No, no, 3e means separately. E comma e comma e.
1 2e and one is
And one is
uh,
e and e.
okay. Yes. Any other thing? Any other?
Uh, I don't think there is any other.
Mugilan, you?
No, sir.
Yes. So that's correct. So first thing, so 7 distributions.
No, here I applied one dirty trick
What?
because nothing is more than 7 in any either of the options.
No, no, no. That shouldn't. That way we shouldn't go. So,
Yeah, I mean, for exam purpose or option test should be a skill, no?
no, that will bring you to a certain level. But if you know these things in a certain way, then that will
Yes.
be always be helpful, because nothing, not everything is like is based on MCQ, right? Life
Yes,
is
yes. I
beyond
mean,
life is beyond MCQs. So that's the thing.
no, I'm just,
Yeah,
I
yeah,
just.
yeah, 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 yeah. I understand. Sometimes you have to do that thing also. Now
Yes.
ways. Okay. Now this is the microstates. Okay. So for this thing, how many ways can be possible? Remember,
Five, five.
remember the okay. You said that 5, right? How 5?
So first energy, first, I mean, the first one particle is having 5e energy.
Hmm.
So that, no, there
Okay.
will be only one.
Yeah, yeah. You are saying it right way. So 5e energy is there. So for particle, and particles are distinguishable. So how many ways we can choose like that? That is 5C1.
5c1 exactly.
That is
Yes, yes,
5.
yes.
This one.
This one can I apply the reverse trick that three energy levels should be empty.
Yeah, yeah, yeah. Same thing, same thing. I have done
So
this kind of problem, right? Here also I have
yes,
done
yes. So 5C3
5C3
into 2,
into 2. Why 2?
because the 4E and E can interchange.
Yes. Here
Here 5C2 into 3,
why 3?
because there are three possibilities. Like 3 can come to first E, second
Yeah.
E,
So you have to choose like
1, 2, 3 is
3C1.
yes,
Yes.
yes. So 1, 2, 3. So 1, 2, 2, 3, 1, 3.
Yeah. Here
Here 5C3 is all right,
5C3 times
and
2. 2.
2.
This one. This one same like
5
this one. This one same like this.
hmm, 5C2 into 3C1. This one to only one.
This
That
one only
second
one.
best.
This one
5C1 into 4C1.
into think about it. The trick is this thing and this thing are similar. Can you say that this way and this way both are similar? Sorry, this way and this are similar. Can you say that?
Yes, we're just breaking the energy levels into
Yeah. So 0 will be E, 0 will be E, and 0 will be 2E, right? Same thing, right? Or 0 will be 3E, same thing. So this will be then 5C2 times 2. Now if we add that, this will be 5C3 means 10 into 2. 10 into 2 means 20. This will be 5C3 means same thing. 10 into 3, 30. This will be 20. This will be 30. This will be 20. So what will be the number of arrangements? 30, 30, 60, 120, 126. So
see last one, that 2E comma E comma E comma E 0.
yes.
So you just converted the last one into the fourth one.
Yes. So not the fourth one.
Third one.
This one. Can you see my laser pointer?
Yes, is last one.
This one, and that one. All three are same. You can see like this. Same thing. 3 has similar energy state and 2
Oh,
different.
acha, in that way.
So these are the pretty tricky thing. We have to be careful. So
I thought you just divided the big thing into small sub
yes.
units, but that
So
is not the case.
this will be 126 ways. Okay. So this is the correct.
Last one, can you say once again, please?
This one.
Last one.
Okay. So if you see this distribution and this distribution, these are called similar, not this called similar or equivalent. Why similar or equivalent? Because here 3 energy levels have same energy. Here also 3 energy levels have same energy. 2 levels are different energy. Same can be applicable here. 3 has different energies and 2 has different energies. So 3 have same energies and 2 have different energies. So that's the thing, right? So is it clear?
Okay, so you just took the thing that out of 5, 2 has same energy, so 5C2, and 2 time they can interchange, so
No.
5C2 into 2.
Out of this, 3 have same energy. So 3 choosing 3 or choosing 3 from 5 and choosing 2 from 5, same thing, right? If you choose 3 out of 5, then 2 will be automatically choice. automatically picked up. And if you choose 2, then 3 will be automatically picked up. Is it clear?
But yes, 5C2 and 5C3 both gives the same values.
Yeah. Any other confusion regarding this mapping or similarity?
No, the last one was tricky. Apart from that, everything is all right.
No, not. Yeah, it is tricky, but you have to, like, to solve the problem. You have to be little. You have to be little bit clever and skillful, because now after giving you this hint, it should be clear, right? Here,
Yes, now it is clear.
yeah, now it is clear, right? Because
Now it is.
you have to see that 3 energy levels have same energy. Here also 3 energy levels have same energy, and rest 2 have different energies.
And
Rest 2 has different energy. Same thing, right? Okay. Now can I proceed to the next problem?
yes, sir.
Okay. Okay. So next problem says 9 particles are to be distributed among 5 energy levels. Both particles and energy levels are indistinguishable. In how many ways can this be done? Can you say? Can you attempt it? Hello, am I audible?
Yes, sir, you are audible.
Is the problem clear? 9 particles and 5 energy levels.
High energy levels, yes.
All are distinguishable.
They, no, indistinguishable.
Indistinguishable. Yeah.
So there is no barrier like 5E, 6E, total energy should be this and that. No barrier. And no occupancy barrier also. So this is a pretty simple question. 9C5.
935. Why? 935. Why?
9C.
Why?
Because 9 particles and 5 energy levels.
Yes.
So no, that logic won't work.
Do not go into the options. Okay. Options may be incorrect. I'm giving you that hint.
So we have to solve it in that way. How many energy levels would be empty or in that way?
Yeah, it can be empty, right?
Yes. So it cannot be also because the number of particles are more than energy
Yes.
levels.
So now from this distribution, this can be like the Bose-Einstein distribution, right?
Yes, is B statistics.
Yes. Now I have given you enough hints. If you want to,
So
okay, let me try it, because anyway. Let me see that video is being recorded or not. Okay, so this thing is, so here in boson statistics, the formula is if there are n particle and g energy level, then that can be distributed as n plus g minus 1 factorial n factorial by g minus 1 factorial. But as you have already known the fact, I do not believe in only the formula. I want to know what is the deepest concept locked up in this counting. Now, in boson statistics, there is no limitation of how many particles should be there in one energy level. Okay, let's say I am giving you 5 energy levels and 9 balls. Okay, this can be distributed like this, where it's the main interpretation of this thing can be like how many balls will be before that. So here we can say that in one energy level there is 1 particle, one energy level there is 3 particle, one energy level 2 particle, one level 3 particle, and another level it is empty. Now it can be like this, that you have to fix one thing, you have to fix one energy level, and you can distribute this object in how many ways it can. So if there are, now you just mix the energy level and particle in just one way, means like the particles level and particle level and energy level and particle both are same in same quantity. That would be how many ways they can be distributed. So they can be distributed like, if there are n particle and g energy levels, so there would be always this way, because one object you have to keep it fixed, right?
You have to take a reference.
So this is the way you can possibly arrange. Now if there are n particles in between that, they can distribute it in such a way that in n factorial way, right? That's why this n factorial comes, because you have over counted it, and there will be g minus 1 thing, because you have fixed one energy level, and then rest of them can distribute it in 4 factorial way, because you have just calculate. Why so? Why is this coming? Why is it coming? Can you say? Can you answer it? Why is it coming in factorial g1 minus 1 factorial? Why is it coming?
Because in factorial, because the number of particles are n, and g minus 1 because we have taken a particular energy level to be fixed. So g minus 1.
That's true. But it is coming because we have over counted here. We have counted that there can be n plus g minus n different objects, and that's why they are being distributed. Means different means they are distinguishable, but they are not distinguishable. They are indistinguishable. So to break that distinguishability, we have to
Divide by n factorial.
reduce it. Okay.
So if we don't give the n factorial, that becomes for distinguishable particles, that follows MB statistics.
Exactly. Now this is the same thing. All the things are indistinguishable. So this will B statistics will follow. So now n is 9, g is 5. So that will be 13 factorial divided by 9 factorial divided by 4 factorial. And if you do that, 13, 12, 11, 10 divided by 4 times 6, so 5, and this becomes how much? Please do the calculation. 715.
715.
So the options are incorrect. Okay, it will be 715. Is it clear?
Yes.
Mugilan?
Yes, sir. Clear, sir.
Yeah. Okay. So you have to dive deeper into the concept so that you can grasp that, and then you just play around the problem. Now, after attending this session, if you solve like 10 or 20 problems in the coming week, then these things will be more clearer, because then you will face different kind of problems, because there will be different kind of situations, different kind of entity. So then more you encounter the different kind of problems, more you will feel comfortable. Okay, so let me just go to the next problem, and we will take, after that we will take some break, 5 or 10 minutes break. 5 not 10 minutes, 5 or 2 to 5 minutes break. Okay, this is one good thing. Question says, okay, question says, what is the expression for ln of W total, where W total is the number of ways, number of different, it called sometimes multiplicity, when n distinguishable particles are to be arranged in 3 distinguishable states. How can you do that? N distinguishable particles are to be arranged in 3 distinguishable states, or everything is distinguishable.
So here MB statistics will work.
Yes, MB statistics will work. Then how can you do that?
So we just remove the n factorial.
No, not like that.
I mean, you are asking in physical sense.
Physical sense. This is same like coin tossing, right?
So 3 possibilities are there.
Yes. 3
3 to the
possibilities.
power n.
Yes, that's the thing. Very easy.
The n ln 3.
Yes. 3 possibilities for each particle. So for then W total for one particle will be 3. The W1 for one particle will be 3. For two particle will be 3. For second particle, for third particle will be 3. Then total will be 3 times dot 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 in time. That will give you 3 to the power n. So ln of W total will be n ln 3. Okay, it is pretty simple, right?
Yes.
Pretty simple. Okay, is it clear, Mugilan?
Yes, sir.
Okay,
See,
thank you.
this thing I was talking about, that approach, the dice where, I mean, the previous one was not related with dice and all, but
That's
this
why
one was.
you just became confused
Uh,
little bit. Yeah, I know. You have to understand, because this problem and that problem, this problem and this problem has fundamental differences, because here the problem is energy levels are indistinguishable and particles are also indistinguishable. But the first thing we can write, the n plus g minus 1, this thing, here we have to choose out of that, and that there it is happening multiple kind of ways. So we are not mixing these things two up.
yeah, because since the particles are indistinguishable,
Yes. So
so
we are choosing. So here we have just, it is not like we are choosing out of like there are 5 energy levels and 9 particles to be distributed among them, and they are all distinguishable. Not like that. We are made the problem in such a way that we just made that there are total n plus g minus 1 object, and how many ways they can be distributed here, means how many ways they can be arranged, not they can be put in some boxes, right? And after doing that, we got to we have this. So there's fundamental difference.
So here we are just asking about the distribution.
Yes. Here we not worried about how many like when just we include the energy levels to the particles, that's why you can write n plus g minus 1 factorial, right? This is like the same problem of like we have fixed 13 positions, like position is fixed, and there are 13 positions, and there are 13 objects. How many ways you can fill these 13 positions? This is the problem, is like that. This is one-to-one correspondence, and this problem is different. This problem is in one position can be 3 particles also, right? Can
Since
you
the
understand
particles
the
are
difference?
indistinguishable.
Yes, here the distribution means 13 positions is there and 13 objects are there, and 13 objects are distinguishable objects. When we are calculating this is distinguishable. To make it indistinguishable, we are making this, but here the problem is there are 13 positions, 13 particles which are distinguishable. How many ways can they be distributed? That is n plus g minus 1 means 13 factorial. And to make it indistinguishable, we have to divide it by this thing. And here difference is different. Here problem is position is 3, but in one position can be 3, can be n particle, right? Is it understand?
Yes. So in the first question, in the previous question,
Yes.
that where we apply the formula,
Yes.
if the particles were indistinguishable, so that would have been 5 to the power 9.
Yes. Distinguishable and no restriction, that should be there. Means any particle can be anywhere.
Exactly.
Right? Okay.
Yes, sir.
So can you you understand the difference, right? Here the problem is there are 13 positions, lattice positions. You have to place these 13 objects in that positions one by one. You cannot put more than one in that lattice position. Here like this.
So indirectly there is a restriction.
Yeah. Right. Because we have made the problem like this to understand how this formula is coming.
This is that minus 1. I have a way of thinking this.
Yeah.
Let's see, there are 5 energy levels.
Yes.
But the gaps are 4.
Yes,
that's why that minus 1 came.
Yes, that's the thing. That is gaps are 4. That's the thing.
So
but here,
is it right? Is the approach right?
Yes, that's the thing. So gaps are 4 means there will be always 4 partitions.
That partition function or all those stuffs.
No. That not that partition function. Means if there are energy levels, 5 energy levels, and you have to let's just draw it, okay? How many boxes are there? 5.
Yes.
So means like 5 boxes means 5 energy levels.
5 and 4 partitions.
4 partitions. So like this, okay? That's the thing. Okay. So please then tell me this answer. This is pretty simple. Tell me. And after that we will take some break. 1 minute or something. 5 minutes.
This will be 6 to the power 3.
No. You are just messing it up. think about it. What is written there? 6 units of energy. Total energy is 6.
6 units.
Mugilan,
Okay.
can you solve it?
Okay.
I can give you some hint.
This we need to solve in the previous way, like 0, 6, 0, 5, 1, in that way.
Then,
The 6, 0,
then tell me.
6 units of energy is there. So 6. So let's say 0,
0?
40, in that way 6e.
6C?
Yeah.
No.
No, I'm saying that in the energy levels are in that order.
Okay. So you have to do it. So you are saying?
At first we have to distribute the things, then find the number of ways.
Yes, distribution. So first thing is
6e, 000.
6e,
Sorry,
0.
0.
Then
5e, e, 0.
5e, e. Then
4e, 2e, 0.
4e, 2e, 0. Then
4e, e, e.
4e, e. Then
3e,
3e.
3.
Okay. 3. Okay.
Then 3, e, 2e.
3,
e, 2e, or 2e, e.
Then any other?
2e, 2e, 2e.
Okay. Any other?
I think if I do any other, the previous ones will only come.
1, 2, 3, 4, 5, 6, 7. Yeah. That's
Is it
true.
right, the distributions?
Distributions, let me check with my answer. 1, 2, 3, 4, 2, 6C. Okay. Yeah, complete. Now this is the distribution. So sub distribution. What will be the ways?
61.
This will be 61. Okay, good. This one?
So there are 6C1 into 2.
61. Why 61?
62 into 2.
Why 6? Why 6 here? This will be 3, right?
Sorry.
Here? 3C2?
3C2 into 2.
3C2 into 2. Here?
Here also same thing because all the three are different.
Here?
Here it will change.
Yes. How?
2 energies levels are of same energy and one is different.
Okay, so choosing one means other will be fixed, right?
3C1. Yes, 3C1 into 2.
No,
1, sorry. 1.
Here?
Same thing. 2 same, 1 different.
Yes. Now you have understood, right? This one?
This one be like everything has an energy.
Yeah.
So
3 times 2 times 1.
1.
That is 3 factorial, right? This is the classical
It's
problem.
only 1.
So
one.
it is. So this is like the same thing. So these two things, let's say 3e, 2e, e, both are distinguishable, right? Means the different things, and you are given only three sides, 3 positions to fill. How many ways they can fill? That is 3 factorial. That is the same thing right here, right? Same thing here. There are ng minus 1 objective, how, and ng minus 1 places. How many ways they can fill? Ng minus n plus g minus 1, they are distinguishable, but they can fill because this is one-to-one mapping. That's why factorial is coming. Here is so same thing. Got my point? Here, this one?
Only one.
Only one. So this is 3.
3.
This is 6.
3CT.
This is
6.
6. This is
6.
3. This is
3.
3.
3.
This is 6.
6. 1.
How many ways then it is happening? 9 plus 18, 27.
9 plus 8, 27 and 28.
Okay.
Option C, yes.
Okay. Okay, then we will take 5 minutes break. Okay, then we will join.
Okay.
Hi, welcome. Everyone there?
Yes, sir.
Yes.
Good, good. Okay.
Sir, like that second last one, can you explain once more?
This one?
This 3 2e, that energy, that number of ways of that distribution.
Okay. 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 So let's say you have three positions, okay, and you have three objects. Let's say this one. How many ways this can be placed? This is three possibility. Now, if it captures one position, how many positions left for this one?
Oh, acha, acha.
Two, one. This is
This
the
is
thing.
similar to the previous week's that deck of cards problem.
Yeah, and this is also similar to this problem also. What I am trying to say, what I was trying to say, because there are 13 positions, and you want to place that 13 different different objects in that 13 positions. That is 13 factorial, right?
So
But
if
since
one gets filled, the other one, I mean one minus one should be there. That minus one term should be there.
that -1 is coming from, because we have to fix one thing, right? Because there are different there are 5 energy levels, there will G energy levels, there will be G minus 1 partitions, because this is the thing, right? From there -1 is coming, but the basic concept, like distributing this factorial thing, it is coming like this. So after calculating those things, like number of partitions and number of particles, that will be n plus G minus 1 total number of objects, and that n plus G minus 1 object will have to be distributed to this n plus G minus 1 positions, and this n plus G minus 1 objects are distinguishable. How many ways we can how many ways we can distribute? That will be n plus G minus 1 times n plus G minus 2, then n plus G minus 3, like this. Okay, this is clear.
Now it is clear.
This one is different. This one is coming from the partition. After
That
calculating that thing,
reference that we were taking.
after that it is a similar thing. Okay. Now
Yes, sir.
let's go to the next problem. This problem says for 4 coin flips, for each distribution of probabilities, PHPT is given 0, 1. PHPT means probability of getting head and probability of getting tails. 0, 1, 1 by 4, 3 by 4, half, half. Which one has the highest number of microstates? How will you do it?
Distribution microstate means the number of ways that can happen.
Yes, yes.
So first one will definitely not be the case because there is only one case.
Yes.
Second one, 1 by 4, 4 coin flips.
Yes. What will be your answer? Tell me. So here, if you probability 0, 1 means there are 4 coin flips. So number of heads is 0, number of tails is 4.
0,
Number of 0 is 4. Here number of heads is 1, number of tails is 3. Here 2 heads, 2 tails. Now how can you distribute this? Number of heads 4, that can happen only once. How can it be? This will be how can it be happen? It can happen at first, or the second time, or the third time, or the fourth time. This is 4C1, and this way, this will be 4C2 times 4C2.
Which, with respect to which
Or
microstate
4C2.
would be this?
Which respect to? I didn't understand your
With,
point.
with respect to which macrostate you are writing this microstates?
No. Microstates means number of possible ways they are being arranged or they are being distributed. So if
I'm telling that with respect to which probability you are writing the microstates.
no. Here the probabilities are given, right?
Huh.
Here the total number of trials is 4. Now if the probability is 0 for head and probability of tail is 1, means always tail comes. How many times tails come then? 4, and
Hmm.
head 0. And if the
Hmm.
probability is 1 by 4 for head, then in the 4 number of trials there will be only 1 times head comes and 3
And
times
3 times tails.
tails
Yes.
come. And here
Hmm.
since the probability is half and half, then number of trials means 2 times tail come appears and 2 times head
Head.
appears. Now
Hmm.
this is the distribution, right? Means
Hmm.
4 tails no head, that can happen only one, mean only one possible ways, and one head 3 tail can happen four possible ways, means like this: head, tail, 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 head, tail, tail, tail,
Hmm.
tail, head,
41.
tail, 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 head. Now here this 2 this can happen 4c2 ways, right? Means head,
Two heads. Out of
tail,
four,
tail,
two heads. Yes, yes, 4C2.
tail, tail, head, head,
Head, head,
tail, head, head,
head, tail.
tail, tail, head, tail, head,
Hmm.
tail, head, then another one,
Head, tail,
tail, head, head.
head, tail.
That is there.
That is written.
So it can happen like a head, tail, tail, head, right?
HTTH.
Then head, tail, head, tail. These are the possible
Six.
ways.
Yes, 6. So that will be the answer.
Yes. So that is
4C2. That's
4c2.
last one. A third one.
Now,
Sorry.
so this is a one way. Now, one way I will teach you. This is the advanced way. So you know entropy S is defined as K ln
W.
W. That is microstate, right? And it is also written as Pi minus Pi ln Pi. Why? Pi is the probability of occurring that event. Here that summation will be over head and tail, because occurring head there are only two possible ways, means there are two possible outcomes, head and tail. So this summation over will be possible outcomes. Is it understandable?
Hmm.
So for which this will be maximum that have highest number of microstates.
Hmm.
Do you agree with it?
Exactly, because PIs are constant, because head and tail, these two possibilities can also be there.
Okay. No, that is not constant because that is given here. So for the first possibility, Pi is 0, means pH is 0, so that will be minus pH ln pH minus p tail ln p tail. This is the formula, because here the summation is over number of outcomes, number of
Head
possible
and tail,
outcomes,
two
head and
outcomes
tail.
are there.
Okay, so for first possibility this will be 0, right?
Because pH is 0.
No, pH is also 0 and pt is 1, ln 1 is 0, so total will be
Exactly.
0. So second option will be minus 1 by 4 ln 1 by 4 minus 3 by 4
3/4 or ln 3/4.
ln 3 by 4. This will be minus half ln half minus half, means if you times 2 then will be minus ln half only, right? And do the calculation and tell me which is the maximum.
Minus ln2 is 0.643.
Minus then.
And no, sir, 2 to the power minus 1 that will be. So
Okay,
minus 1 is a plus.
so that will be
So
0.
that would be 0.643, I guess. Let me check.
0.643. or 9.3?
693, I think.
Okay. I hope it is.
0.693.
Yeah, yeah,
693.
yeah.
693.
That is also I remember 693. And this one?
This one, let me do it once. One minute.
Do it.
It's coming 0.551 or
So
552.
so that is
Around.
less than that, right?
Yes, yes.
0.5623. For me, it's coming 0.5623. So this is maximum, right?
Hmm.
That way you also do. So this is a smarter way.
Yes,
Okay.
because that requires a lot of a
Calculation.
lot of things to keep
Yeah.
in mind.
Yes. Yes. So this is the thing. Okay. This is the definition of the entropy from probability. Okay. I told I told you in the beginning. I think that probability theory is always important in thermodynamics and statistical mechanics. Here it comes. So I will give you some flavors because I cannot go beyond some difficulties because that will not do justice to your levels right now. But this is the thing. So you will remember this formula is minus pi ln pi, and that summation is over all the outcomes. Okay.
Yes.
Okay. Okay. Let me go to the next problem. Next problem says there are 4 aces in deck of 52 cards. If you pull a card and return the card, then reshuffle and pull a card again, how many ways can you pull just one ace in the 5 pulls? Answer me. This you will answer. I will not give the answer. You will answer and
This means that one, no?
the one means no. That said that how many ways can you pull just one.
No, 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 no. Ace is that ace card is on one, no? One, two, three. That one is ace.
Ace is A
Ace
means
is that ikka.
A. Okay, just tell me answer or think about it and then tell me.
So 1/13 into 1/13 in no. Yeah, I'm thinking in that way that there are four aces,
Yes,
52 cards are there.
yes, yes.
So, so probability of getting one ace out of that 52 cards is 4/52.
No, that is you are talking about probability. I'm saying about
Ajay,
the question says
how
that
many
how many
ways?
ways. But it's simple. You are making it complex. Just think you are pulling one card and after pulling that you see that result and then you keep it there and then reshuffle it. Then how many ways you can pull just one ace after 5 pulls? This is pretty simple. You have to answer it. Think about the question. Is it visible? I will make it
Yes,
bigger.
this question is feasible.
Okay.
So can we compare this to a 52 faced die?
I'm saying again, you are complicating it.
I think only one is the answer. How many ways can you pull one? Is it's one.
How?
Because there are 52 cards.
Let me just state the problem again. There are 52 cards and 4 aces in 52 cards. Okay. If you pull a card, then return the card, then reshuffle, how
No,
many
one way.
ways can you pull?
I think
Just
I think on 5 ways.
yes. These all are just rubbish thing. This is nothing. This doesn't have any meaning.
Hmm.
So it can happen.
Can I explain?
Yeah.
So 5 ways. I mean, I have only 5 chances.
Yes, that's the thing. So you
So
can pick it up for in the first attempt, second attempt, third attempt,
second attempt,
fourth
third
attempt.
attempt, or fourth attempt, or fifth attempt. Yes,
Yes,
five.
that's the thing. So
Now I'm getting to know the flavor. I mean, I'm
yeah,
getting the taste.
we can pull just one ace in 5 pulls in the first attempt or second attempt or third attempt or fourth attempt or fifth attempt. So ways would be 5. Okay, it's pretty simple. Do not make it complicated. Okay.
Sir, I have a doubt.
Yeah, please.
Sir, what if the card we took first is the card we need to draw?
Yeah,
Like, what
that.
is the probability that we will get the same
Yeah.
ace?
Yes. So then the probability that is about probability. Okay. So then probability will be, you are saying that the if I understand your question properly, that uh, what is the probability of getting ace at each attempt? Is this your question, right? Hello.
Um, Sir, actually, it is like we are replacing the ace, right, sir, at the first attempt.
Yes.
So, and after reshuffling, what is the probability to draw the same card in just one try?
In
It's a
just
different question, not the yes,
yeah.
not
So
related to this one.
okay. So let's. So the probability of getting ace at first attempt is 4 by 52, means number of ace divided by total number of cards, that is 1 by 13. Okay. Now in a second attempt, the probability of getting ace is also same, because you just put the card there, 4 by 52, that is 1 by 13. Now if you say that what is the probability that you get uh, ace at first attempt and also get ace and second attempt, then the probability will be 1 by 13 times 1 by 13. Is it clear?
The answer that I gave at first.
Yes, sir.
Is it clear? Is this is
Yes, sir.
okay? Now that is for one ace. That is for one ace actually, means that is for ace. One ace, that will be 113 times 113. It is the probability of getting same card consecutively. That is your question. Consecutively. That is the answer. Okay. Okay. Next. This is a problem. This is quite interesting problem, and if you solve this problem with the knowledge, then I will be pretty happy. Problem says your statistical mechanics class has 25 students. Okay. What is the probability that at least 2 classmates have the same birthday? Let me give you one disclaimer that here no leap year, only 365 days that you have just taken into account. Now tell me what will be the probability, or how you are gonna approach the problem. Think about it for 1 or 2 minutes.
So minimum 2 classmates must have the same birthday.
Yes, minimum.
Sir, I think
Yeah.
we can calculate that what is the whole probability. Then
Yes.
we can just subtract what is the probability that means at least 2 classmates do not have the same verdicts like that.
Yes. Yes.
So that
That is excellent. Excellent. That is the way. So as Mugilan said, that is it like the probability of at least, let's say 2 birthday, probability of at least greater or equal to 2, let's like it is same as total probability is always with 1, right? Minus, he said that probability of uh, no person have same birthday, no person have same birthday, as Mugilan rightly said. So we have to just, so all agree with Tathagata, you are agreeing with it?
Absolutely.
Yes. So now we have to calculate this thing. What is the probability of no person have same birthday? I am denoting as P0. Now there are 365 days and 25 students, and this is classical permutation problem, or combination problem, where, or let's say permutation problem, where we are saying that these 25 guys do not have same birthday. So what is the let's say first student, what is the how many possibility of his or her choosing her his or her birthday. That is 365,
Oh,
right?
365 into 364 into 363.
Then 364
Uh,
dot 25 student means 3 6 350 340
341.
1, right?
Hmm.
This is the possible way divided by total number of possibilities. The total number of possibility, how many possibility can happen? This is can happen same dice problem, 365 dice face.
To the power 25.
Yes. Okay.
Huh.
So probability of getting more than 2 or 2 birthdays is 1 minus 365 dot let's say 364 dot 341 divided by 365 times 25. Okay, so please calculate it for me.
It is coming around 58%.
15%.
Like 58, 58.
Yes. So 1.
Like 57.8 something, so
Okay.
58 can we can.
So this is coming near about
That 1 minus that thing is coming around
0.578.
44.
Then it will coming as 0.578, right?
No, 0.4.
No. Total. 1 minus this thing. That is the
And
probability.
1 minus that thing is 0.5%. I'm talking about
Yeah.
that
Acha.
only multiplication and division. That is
Okay.
0.44 something.
Okay.
So automatically that becomes 0.578
Hmm.
something range.
Okay. So that's the thing. So 58%. This is the nearest thing. So let's not fight about the 1 decimal point. So that is the answer. So this concept is clear, right?
Yes.
Okay. Okay. So the next problem. Next problem says, if you have a one-dimensional lattice that contains Na particles of type A, Na number of particles of type A, Nb number of particles of type B, they completely fill the lattice, so the number of sites is Na plus Nb. Write an expression for the multiplicity, means number of ways to choose, of distinguishable arrangements of the particles on the lattice. This is pretty simple. This is very simple. You should answer it. Anyone? Anyone?
Is it Na plus Nb factorial by Na factorial by Nb factorial?
Yes, it is. Why
Okay.
so? Why so?
Um, it's like the same thing, like total by the ways we can arrange.
Yes.
The
So
same thing.
yes, yes, true. So the way is like, as Mugilan said correctly, that so there are Na plus Nb sites. Now, since Na plus Nb sites, that can be arranged as Na plus Nb factorial, right? Now we have calculated Na plus Nb factorial, right? Now in the problem that I have solved previously, since these lattice sites are not distinguishable, so we have over counted it. Now we have to cancel how many number of A particles is there and how many number of B particles is there, or we can write as Na plus Nb this number of sites, and from that we have to choose Nb sites where we can put B type of particles, and if we choose where we can put B type of particles, we will automatically choose where we can put A type of particles, right? Because since number of total sites is Na plus Nb, so
If we can define one thing, the other thing will automatically be
automatically
defined.
comes. So that's why this is Na plus Nb factorial divided by Na factorial by Nb factorial.
Into any factor.
So option number this. Okay. Okay. So few further problems. Problem number 1. How many arrangements are there of 15? Let's mark it. 15 indistinguishable lattice gas particles distributed in 17 sites. Please answer it, because I have solved many this kind of problems. Please answer it. Take 1 or 2 minutes and answer me. This is indistinguishable also.
Option B.
Option B, yes. Mugilan, do you agree with it?
Actually, I'm just calculating.
Yeah, you
Like
calculate. You calculate. We will wait.
okay. I think I messed up, sir.
Yes.
I'm not getting the answer.
Answer is
No, sir, I think I messed up with something. I'm not getting any answer.
okay. Okay. So just no. Here the correct answer is there. So let me just do it. So as how can you do it? It's the same thing. So there are 17 sides, 15 gas particles. Now choosing, and also that they are indistinguishable. So this problem actually comes like choosing two vacant site.
Yes, I applied this logic onto.
Yes.
Two sides should be vacant,
Out of
so it will
17.
be 17. 17
So
C2.
17 C2, that will give you 17 factorial, 15 factorial, 2 factorial, and it makes 17 plus 16 by 2 factorial, that makes 196. Is it okay, Mugilan? Is it clear now?
Yes, sir.
Yeah, thank you. Okay, let me go to the next problem then. This problem says if there are 5 distinguishable degenerate energy levels, okay, 5 and distinguishable, and on top of the degenerate 12, and also 12 distinguishable particles, in how many ways can they be arranged in such a way that there are 6 particles in the first level, 3 in the second level, 2 in third level, 1 in fourth level, none of in the fifth level. Let's say like A, B, C, D, E. So at A there are 6, in B there is 3, in C 2, in 1O 1, in D 1, in E nil. Now these are distinguishable, right? These energy levels. For fast, how will you do it?
12C6.
12 C 6. Why?
Because there are 12 particles, out of
Yes.
which 6 particles we need to select
Yes.
for the first level.
Yes.
So there is no constant, so we can directly select 6 particles out of those 12.
Yeah. Actually, it comes like total number of possibilities will be for 12 distinguishable particle is 12 factorial, right? Total number of possibilities. Okay. Now, how many ways this 6 particle can distribute? That is 6 factorial.
Yes.
How many ways these 3 can 3
3
factorial?
factorial,
This
2
is 2
and 1.
factorial. This is 1 factorial. Now, out of those 12, this is this thing which can happen from here. Okay. So the answer will be, this is the classic Maxwell-Boltzmann distribution. W total is 12 factorial by 6 factorial by 3 factorial by 2 factorial by 1 factorial, or it can be written as n factorial divided by product of I equal to 1 to n, that is n factorial. Here it means n total number of particles and n means number of particles at n levels. That means here there will be for one level that is 6, second level 3, third level 2, fourth level 1, and fifth level 0. So is it okay, this thing? This is understood, this formula, how
Yes, sir.
it is being written.
Yes, sir.
So if you do that, please tell me the answer.
At 55,440.
Okay, so this is the correct answer. Okay, so let's just speed it up. I got few minutes left. This option, problem number 3. Problem number 3 says a sample consisting of 5 molecules has a total energy of 5 epsilon. Each molecule is able to occupy states of energy J epsilon, where J takes the value 0, 1, 2. Now calculate the weight of the configuration in which the energy is distributed evenly over all the molecules. Here the term weight means how many ways we can distribute this configuration. Please tell me the answer. This is pretty simple, right? Anyone?
That means all the molecules must have same energy.
Yes.
Only one possibility is there.
Yes. Mugilan, do you agree with it? There will be only one possibility.
Yes, sir.
Yes. 5 molecules. Total energy 5 epsilon equally distributed. So everyone has epsilon amount of energy. So number of ways will be 1. So weight factor. Okay. Okay. Let me go to the next. Now these things. What is the total number of microstates possible in the question 3? Question 3 means this thing is not there, means a weight, this thing is not there. The system means like sample consisting of 5 molecules has a total energy, each molecule is able to occupy states of energy this. Now how many ways they can be distributed? Is my question clear? The restriction is not there. Now the equality distribution and all those things, this is lifted. So if I write this thing in this way, 5 particles distributed in total energy equal to 5 epsilon, and individual energy they can take J epsilon, where J belongs 0, 1, 2 integer energy. Please tell me, you have did this problem today only, you have did this problem. Tell me where we have done it and what is the answer.
So you have to just write those things, the possibilities.
No, that is true. I means we have done this problem, where we have done this today, we have done this problem.
Sir, like we are going to write like 5, comma 0, 0,
Yes,
and we are calculating. Yeah.
yes. So here this problem and that problem is similar, right?
Yes, sir.
So now taking clue from this problem, that is simply writing is, so how many ways we can write is 0, 0, 0, 0, 5 0 0 0 1 4. Should we do it, or we can refer to the problem number 3?
Yes, we can refer.
Mugilan,
Yes, sir.
should we do it again, or we can refer to the problem number 3?
I think we can refer, sir.
Yeah, okay, thank you. So problem number 3. 1 to 6 ways. So this is now last question of this session. Determine the number of ways in which 5 indistinguishable particles can be put in 7 indistinguishable boxes. So there is 5 indistinguishable particles and 7 indistinguishable boxes. How many ways we can put? Can you answer it? Anyone?
Seven C two.
7C2.
21.
21 is your answer. Okay, let's see others. Mugilan? So 7 balls can be in one. Again, sorry, 7 need 5. 5 particles can be one. 4 or 1 and rest are vacant. Then 3, 2, rest are vacant. Then 3, 1, 1, rest are vacant. 2, 2, 1, rest are vacant. 2, 1, 1, 1, rest are vacant. And 1, 1, 1, 1, and 0, 0. How many ways then it is coming? 7, right? Because these are indistinguishable. Means keeping 5 balls here and 5 balls there doesn't alter the ways. So
No, I approached the question in that way ki there are 5 particles, 7 boxes. So even if we keep all the 5 particles in one box, 2 boxes are going to remain, at least 2 boxes are going to remain empty.
yeah, it will be always there. But you are choosing that 2 box out of thing that is not important, because there will be more than 2 empty boxes for different distribution, right? For here there are 6. So you have did the same mistake in the previous session also. Like sometimes the mapping is not that simple, because in that class also if I do remember correctly, that there also like some kind of a problem was there, and you calculated that the 2 boxes will be always empty. So choosing 2, that is not true. That is not true, because here the empty boxes number is also changing, right?
Yes, it can be more than 2 also.
Yes. So this is the thing. 7. So it is clear, Mugilan?
Yes, sir.
Yeah. Okay. So that's it. Thank you everyone for joining. Any other question? And then we can end this session. Okay. So if not, then we can end it.